Hello and welcome to my science tutorials. In today's video, we want to look at series connected impedances. Before we begin, if you are new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. Now, in our previous videos, we looked at AC circuit, where we look at impedances in an RLC series circuit. Now, in this video, we want to look at what to do when we have multiple impedances, because in the previous video, we only looked at just having one impedance. Now, what if we have multiple impedances? How do we attempt to solve that problem? So let's have a typical example of how our circuit is going to look like. So assuming we have a coil that has a resistor and then an inductor, then we have another coil having another resistor and then an inductor, which is also another impedance. Then we have a third resistor connected to a capacitor. Okay, so this is how our circuit looks like. Alright, so we have resistor 1, resistor 2, and then resistor 3. We have capacitor 1 here, then we have inductor 2, inductor 1. So we are calling resistor 1, inductor 1 our impedance 1. So this is our impedance 1. So we are calling the second guys over here, let me use this, as impedance 2. And then the last one, we are calling this impedance 3. Now, if we are to find the overall impedance of this circuit, which is the total opposition to the flow of the current flowing through this particular circuit, we realize that we can take the impedances one after the other, find the impedances and add and use that as our calculation. We need to rewrite, or we need to do some certain things. Now, if we look at this, we realize we have resistor 1, resistor 2, resistor 3. So the resistors are in series, so we can add all of them to have a total resistance, and we use that in our calculation. The inductor, we have inductor 1, inductor 2, so we can add it. Inductors in series, we can add it, inductor 1 plus inductor 2, to get our total inductance. Then we only have one capacitor, we can maintain that. So overall, our new circuit will look something like this. So we are going to have a simplified circuit with just one resistor, which I'm going to call RT, and then one inductor, which I'm going to call LT, and then one capacitor connected in series. So I'm going to call here CT. Now remember or note that our RT, which is the total resistance I'm writing over here, is equal to R1 from this first circuit, R1 plus R2, the second resistance in the impedance 2, plus R3. So our R total is R1 plus R2 plus R3. Our inductance, or our total inductance, LT, is equal to L1 plus L2. And then our C total in this example is just equal to C1, since we only have one capacitor. Now, what happens if we have multiple capacitors? Now, if we have multiple capacitors, we realize that, so let's say, assuming that, let me use another color to indicate that. So let's say here we have a capacitor, here is also a capacitor, so it's now our C2. How do we find the total capacitance in this case? If this is the case, and in place of this inductor L2 we have capacitor, it means our total capacitance will be different. Now we realize that capacitors in series, we don't add the value, we find the inverse of that. So it will be 1 over, our total capacitance in that case will be 1 over C1 plus 1 over C2, giving us 1 over C total. Let me rewrite that. So it will be 1 over C total is equal to 1 over C1 plus 1 over C2. this will give us, or this is what we use to find CT. We make CT the subject, and then we use that in the new circuit before we go ahead to proceed and look at our total impedance. So with this basic introduction, and knowing very well that the formula for calculating impedance when we have a resistor, inductor, capacitor circuit, as we saw in the previous video, we saw that our impedance is equal to the root of R squared plus SL minus XC, this guy's squared. So this is how we find the impedance in case we have a resistor, inductor, and a capacitor in series. Now, in the previous video, we also realized that depending on whether the capacitive reactance or the inductive reactance is bigger, this guy can either be XC minus XL or XL minus XC. But at the end, since we are squaring it, we're still going to have a positive value. So it doesn't matter which of these guys you bring first, you're going to get the same answer. Alright, so let's proceed and have a look at an example to understand and appreciate what we are talking about. So we have the first example for this particular tutorial. We have the following impedances are connected in series across a 40 volts and 20 k hertz supply. We have a resistor of 8 ohms. We have a coil of inductance 130 microhenry and 5 ohm resistance, and we have another coil with 10 ohms resistor in series with a capacitor of 0.25 microfarad. So we have to calculate the circuit current, the circuit phase angle, and then the voltage drop across each impedance. This is very good. So let's go ahead and look at the solution for this problem. Solution. So the first thing we want to do, or I would do when I have a question like this, is to try and draw my circuit. So I've been told that I have a resistance of 8 ohms. So I know I have, first of all, I have just a resistor. Then it is connected to a coil that has an inductor and then another resistor. So I have an inductor connected to a resistor. Okay, so this is 130 microhenry. This is 5 ohms resistor. The first one is 8 ohms resistor. Then it is then again connected to a 10 ohm resistor. So I have 10 ohms resistor connected to a capacitor of 0.25 microfarad. And then all of these guys is now connected to a 40 volts 20 kHz frequency supply. Okay, so this is the direction of our current. This will not be our this side will be considered as our impedance 1. This will be considered as our impedance 2, and then this will be considered as our impedance 3. So I'm going to use impedance 1, I2, and I3 for them. So this is our circuit. Now we realize that if we look at the circuit very well, we have resistor in the first impedance, we have resistor in the second impedance, then we have resistor in the third impedance. And that is the only thing, or the only component that is consistent or repeating throughout the various impedances. So this entire circuit can be redrawn in a much simpler version as just having one resistor, one inductor, and then just one capacitor across a voltage supply. So we have our current moving in this direction. We have our 40 volts and then 20,000 hertz frequency supply over here. Now our resistance, okay, the total resistance over here, let me make that RT, will be equal to R1, which is this guy. Let me make it R1, R2, and R3. So our total resistance over here, R total, will be equal to 8 plus 5 plus 10 ohms over here. So as we can see, if we add this plus this is 15 plus this will give us 23 ohms. So our total resistance over here is 23 ohms. Our inductor is still going to be the same, 130 microhenry, and then our capacitor is going to be 0.25 microfarad. So this is now a simpler version of the entire complex impedances that we have over here. So this is a simpler version. Now from here we can go ahead and calculate for whatever the question is asking us to do. So the first thing we were asked to do is to find the circuit current. Now to find the circuit current, we know that in this type of circuit, RLC circuit, to find our current, we know that voltage is equal to current multiplied by impedance. So if we make current the subject, we are going to have voltage over impedance. Now we have our voltage, but we do not know our impedance. So the first thing we need to do is to find Z, or our total impedance. So let's go ahead and do that. Now the formula for finding impedance is the root of resistor squared, which in our case will be RT squared, plus into bracket XC minus XL or squared. This means that we already have our resistance, or R total. We already have that, so we are good to go. But we do not know XC, and then we do not know XL. So these things are what we need to find first, and after finding them, we can now go ahead and find the total impedance. So now the capacitive reactance, which we are calling XC, is given mathematically as 1 over 2 pi FC. This means that our XC is equal to 1 divided by 2 pi multiplied by our frequency given to us in this question is 20k. Okay, so that is 20,000. 20 times 10 raised to the power 3, then multiplied by the capacitance of the capacitor. In this case is 0.25 microfarad. So that will be 0.25 times 10 raised to the power negative 6. Okay. Now if we compute this into the calculator, 1 over 2 pi multiplied by 20,000 multiplied by 0.25 times 10 raised to the power negative 6 is going to give me 31.83 ohms as my answer, or as my capacitive reactance. Now the next thing I need to do is to find my inductive reactance. Inductive reactance is given to us by the formula 2 pi FL. This implies that we have 2 pi multiplied by frequency, which is 20 times 10 raised to the power 3, and then multiplied by the inductance of the inductor, which in our case is 130 times 10 raised to the power negative 6 as given in the question. Now if we multiply everything we have over here, we are going to have 16.34 ohms as our inductive reactance. So now that we have our capacitive reactance and our inductive reactance, we can now proceed to find our impedance. So our impedance Z will be equal to, we already stated the formula above here, so this is going to be the root of our resistance. As we saw earlier on, the total resistance over here is 23 ohms, so we are going to use that. So we have 23 squared plus into bracket we have XC minus XL squared, so we have 31.83 minus 16.34 or squared. Now if we compute these into the calculator, we are going to get a total of 27.73 ohms as the impedance for calculating this entire calculation. So 27.73 is now the impedance of this overall circuit that we have over here, this entire circuit, or this circuit. The total resistance, or the opposition to the flow of current in this entire circuit, having the resistor, the inductor, and then the capacitor, is equal to 27.73 ohms. Now that we have that, and we were told that our voltage is 40 let's go ahead and find our current. So our current A or I, sorry, is I. Our current is equal to voltage over impedance. And then our voltage, as we saw earlier on, the voltage is 40. And then we just found our impedance to be 27.73. So 40 on 27.73 is equal to 1.44 amperes. So our current, or the current flowing through that entire circuit, is 1.44 amperes. Now let's go ahead and look at the II aspect of the question. So we are to calculate the circuit phase angle, and then the voltage drop across each impedance. So let's go ahead and look at that. So the second thing we need to do is to calculate the phase angle. Now to calculate the phase angle is equal to tan the phase angle. So tan phase angle is equal to XC minus XL all over R. So this is how we find the phase angle. So this implies that we have theta is equal to the tan inverse of XL minus XC. That is going to give me 31.83 minus 16.34, all divided by our resistance, or R total in this case, is going to be 23 over here. So our phase angle will be equal to the tan inverse of 31.83 minus 16.34, all divided by 23, is equal to 0.673. And then if we find the tan inverse of this decimal, we are going to get the angle 37.71. So our angle here is 37.71. Alright, so now that we found our angle, let's go ahead and answer the third aspect of this particular question. So the third aspect, III or C, is saying that we should find the voltage drop across each impedance. So the voltage drop across each impedance is very, very easy. So how do we do that? So this is the first impedance, like I said, I1. So let's find the voltage drop across I1. The voltage drop across I1, let me get some space. Now, to find the voltage drop across just the resistor, the voltage drop across just the resistor will be equal to the product of the current and the total resistance. So if we go back, we realize that in that case, since this is the impedance 1, we just use just R1 as our resistance over here. So it is IR1. So the voltage drop across the first resistor, or R1, is equal to our current we saw earlier was 1.44, and then our resistor 1 is just 8 ohms. So if we multiply that, we have 11.52 volts as our voltage drop across impedance 1. Now for impedance 2, voltage drop across impedance 2, let me make here 2. Now if we look at impedance 2, we realize that we have an inductor and then a resistor. Okay, so to do that, our impedance will be equal to I, which is our current, multiplied by impedance 2. Now what is our impedance 2? Our impedance 2 here is equal to the root of the resistor squared plus XL squared, where SL is the inductive reactance. We calculated for that earlier on. But in this case, if we look at this that we have, our inductor is 130 microfarad, and then our resistance here is 5 ohms. So let's go ahead and do that calculation. So from here, our voltage drop on the second impedance will be equal to, our current is 1.44, multiplied by the root of our resistor, in this case is 5 squared, plus our XL, okay, we've already calculated that, was 16.34 squared. So if we compute everything we have over here into our calculator, we are going to get the voltage of 24.61 volts as our answer. Now let's look at the voltage drop across the third impedance. So that will be equal to I multiplied by impedance 3. Now what is impedance 3? If we go back, we realize impedance 3 has a resistor of 10 ohms and then capacitor over here. So it's going to be V3 is equal to I multiplied by into bracket resistor 3 squared, okay, plus capacitive reactance squared over here. So our voltage drop 3 will be 1.44 multiplied by the root of, we have 10 squared as our resistance squared, plus we already found our capacitive reactance, and that was 31.83. So we squared that, and then we compute everything we have into the calculator here. We have 48.04 volts as the voltage drop on impedance 3. Now let's go ahead and have a look at another example so that we further appreciate what we are doing on series connected impedances. So the second example that we have is this. We are to determine the potential difference V1 and V2 for the circuit shown in the figure below. If the frequency of the supply is 5 kilohertz, we are to determine the voltage supply and then the circuit phase angle. So this is very beautiful. We already have our circuit given to us, and we're told that we don't know the voltage, but we know the frequency to be 5 kilohertz. So this is very good. This is very awesome. So we have to determine V1 and V2, and subsequently determine V, which is the supply voltage, and then calculate our phase angle. We already have the current in the question. We have our resistor, we have our inductor, another resistor, and a capacitor. Now the first thing we need to do is to simplify the circuit we have over here, because over here we have impedance 1, let me say I1, and then we have impedance 2, this is I2. Now you realize that impedance 1 has a resistor, impedance 2 has a resistor, so we need to redraw this entire circuit. So we are going to have the circuit now looking like this, just having one resistor, and that will have R total, which will be equal to 4 plus 8, and that will give us 12 ohms. Now we now have our inductor, which is still going to have 0.286 millihenry, and then we're going to have our capacitor connected, and that will be 1.273 microfarad connected to an AC source, and then we don't know the voltage, and we still have 5 kilohertz as our frequency here, and then we have our current to be equal to 5 amperes over here. All right, so let's go ahead and look at what we can do. Now the first thing we were told to find is V1, V2, and then find the overall impedance across the circuit. All right, so to do this, the first thing we need to do is to go ahead and find our impedance, which is the overall opposition to the flow of current in this particular circuit. Now to do that, we know that our impedance is equal to the root of resistance square, which in this case will be our RT, plus into bracket XC minus XL squared. This tells us that we need to find the capacitive reactance and then the inductive reactance. Capacitive reactance, we know that is equal to 1 over 2 pi FC. So we go ahead and do the substitution. So we have 1 over 2 pi. Our frequency is 5 times 10 raised to the power 3, multiplied by our capacitance, which is 1.273 times 10 raised to the power minus 6. So if we compute everything we have here into our calculator, we are going to get exactly 25 ohms as our answer. Now the next thing we do is to find our inductive reactance. Inductive reactance is given mathematically as 2 pi FL. This is equal to 2 pi multiplied by the frequency, which is still the same, 5 times 10 raised to the power positive 3, multiplied by our inductance, which is 0.286 times 10 raised to the power negative 3. So if we compute this into the calculator, it's going to give me an answer of 8.985 ohms as my answer for inductive reactance. So let's do the substitution. So our impedance will now be equal to the root of resistor square here, which is going to be 12 squared, plus our XC is 25 minus our XL, which is 8.985 all squared. So if we compute everything here into our calculator, our impedance Z is going to be equal to 20.01 ohms. So this is our impedance for this entire circuit. Alright, so now that we have the impedance for the entire circuit, let's go ahead and find or determine the overall supply voltage over here. So let's go ahead and look at that. So to find the overall supply voltage, we don't know that. We know that our current given to us in the question is 5 amperes, and then we just found our impedance to be equal to 20.01. So the voltage supply, let me use Vs as voltage supply, is equal to Iz, current multiplied by the impedance. So this is equal to 5 multiplied by 20.01. So this will give me a total voltage supply of 100.05 volts as my voltage supply. Okay, so now that I have my voltage supply, I can go ahead and find my V1 and V2. Okay, so let's go back and look at our circuit. Now if we look at our circuit, we realize that to find V1, we need the impedance of I1. We need I1 over here, the total impedance over here. Then we need the total impedance over here. So once we find the impedance here, we can then use it to find the voltage V1 and then V2. So let's go ahead and look at that. So to find V1 is equal to I multiplied by impedance 1. So V1 is equal to current. Now what is impedance 1? Impedance 1, if we look at the diagram, we realize that impedance 1 has a resistor of 4 ohms and then an inductor of 0.286 microhenry. So it means that our impedance is going to be R squared plus XL squared. That will be our impedance for this particular case. So V1 will be equal to 5 for our current multiplied by our resistance was 4, so we have 4 squared, plus we already calculated for our XL and we found that to be 8.985, so we have 8.985 squared. So our V1 is equal to, if we everything we have here into the calculator, we are going to get 49.176 volts as our answer. Now what is V2? V2 will be the same thing, but I multiplied by Z2. So what is our Z2? Our Z2 is equal to the root of R squared. But then we realize that if we look at the circuit, instead of having an inductor, we have a capacitor over here, which has 1.273 microfarad as its capacitance. So it's going to be R squared plus XC squared. So our V2 will be equal to 5 multiplied by our resistance in that particular circuit was 8 squared, plus we already found our XC to be 25, so we have 25 squared over here. So our V2 will be equal to If we compute everything we have over here into our calculator, we are going to get 131.244 volts as our answer for V2. So we already found our total voltage supply. We find the voltage across just the impedance 1 and then the voltage across impedance 2. The last thing we were told to find is the circuit, is to determine the circuit phase angle. So to find the phase angle, you know that tan, the phase angle, is equal to the ratio of XC minus XL all on R. So this implies that our phase angle is equal to the tan inverse of our XC is 25 minus 8.985 all divided by 12, which is the resistance we have as our total resistance we have in the circuit over here. So that means our theta is equal to the tan inverse of the ratio we have over here is equal to 1.3346. So our phase angle is equal to the tan inverse of 1.3346 is equal to 53.16 degrees. So this is how we solve questions on series connected impedances. We look at the various impedances that we have. If we have resistor common to them, we add how we add resistors in series and then write our total. Redraw the new circuit and write the total resistance. If we have inductance that is common, we add all the inductances and then have our total inductance. If capacitor is present, 1 over C total is equal to 1 over C1 plus 1 over C2 till the number of capacitors you have. You add that and get your total capacitance, and then from there you can now go ahead and use these values to calculate for your total impedance and go ahead to find any other problem that the question might demand from you. So thank you so much for watching, and I will see you in the next video. Bye bye.